In this lecture, we're going to review moment of a force. We will learn or review the scalar formulation and vector formulation. The scalar formulation, which is usually used in a 2D problem, while the vector formulation will be applied to 3D problems. And we'll also apply the principle of moments for certain problems. We mentioned in the introduction to this course, force has two major effects. The first one is translational motion when you push a cart going forward. It also has rotational motion. If you want to turn the handle of the wrench, the force will cause rotational motion. So the rotational motion is described by the moment of a force. Moment sometimes is called force moment or torque, is the rotational force. It provides rotation or tendency for rotation. Moment is a vector, which means it has a direction and it has a magnitude. So the magnitude of the moment is directly proportional to the magnitude of the force F and the moment arm D, where the moment arm D is defined as the perpendicular distance from the point O, where we're calculating moment about, to the line of action of the force. So in the figure A, if we're applying the force in a direction that is perpendicular to the line, to the handle of the wrench, then the distance or the moment arm D is just the length of the wrench over here. But if we're going to apply the force in an angle theta, which is not equal to 90 degrees, with the handle, then the perpendicular distance or the moment on the arm may not be D anymore. Instead, it's just equal to, or is defined as, the perpendicular distance from the point O to the line of action of the force F. So sometimes to find this moment arm, you need to extend the line of action of the force, so you can drop a perpendicular line and the measure distance between the point O and the perpendicular point here. So in this case, D prime is the moment arm. It equals to D times sine theta. Or if we pull on the wrench, you can imagine this is what you're going to do. If you want to rotate the wrench, instead of pushing it, we pull on it. So the result is the wrench will not turn at all because the moment arm is 0 now. So the moment F times D becomes 0. In other words, the rotational force becomes 0. So that's why if you pull on the wrench, it will not turn. So here's something we want to pay attention is if the line of action passes through the point, like in this case point O is on the line of action of the force F, then the moment is 0. After reviewing the magnitude of the moment, let's take a look at the direction of the moment. So let's focus on the 2D example. So by saying 2D, we mean the force F and this point O is within the same plane. Or we say the vector the moment arm D and the force F is within the same plane. We have a 2D. Or if you take a look at the trajectory of a force of a particle moving around this circle is a 2D, is in a 2D plane. So this is what we say, a 2D. So if that's the case, and the direction of the moment is described by the moment axis. So this moment axis is perpendicular to the plane. So now you see this line marked by M sub O, that's the moment axis. This moment axis is the direction of the moment, and it is perpendicular to the plane that contains the force F and is moment arm D. So figure A is the side view. From the side view, you can see there is one vector, MO. It's a line with certain magnitude, and the magnitude is F times D, and the direction is pointing up. And on the bottom, this is the top view. So if you, think about this is a piece of paper and you look down from the top to the paper, then you just see a plane. So this force F is in the plane and this D is in the same plane, or you can draw this line on your paper, D on your paper as well. And the other vector, MO, it becomes a point because it's pointing out of the paper. And the sense of rotation and the moment axis is defined by the right-hand rule. The right-hand rule is if you curve your forefingers in the direction of rotation, your thumb will point to the direction of the moment. In 2D, the direction of moment is either clockwise or counterclockwise, depending on the tendency for rotation. On the left-hand side, we have a force with a magnitude of F, and the moment arm is D, perpendicular distance from the point O to the line of action of the force F. So the magnitude of this moment is F times D. And this force will cause a clockwise rotation about the point O. We can use right-hand rule to prove the direction of rotation. You can extend your forefingers on your right hand in the direction of D. So extend your forefingers along the D. Then curve your forefingers in the direction of the force. Now, the direction of the curve indicates the direction of rotation. On the right-hand side, we have the same force, or actually the force with the same magnitude but opposite direction, and same moment arm D. So the magnitude of the rotational force or the moment is the same, which is F times D, but the rotational direction will be opposite, which is clockwise. So there's a sign convention for moment, especially 2D moment, is counterclockwise rotation is positive and clockwise rotation is negative. The principle of moment states that the moment of a force about the point is equal to the sum of the moment of the components of the force about the point. So for example, if we have a force F applied at some point over here, and we can resolve the force F into two components, F1 and F2. So F equal to force F1 plus F2. Then the moment of the force F about the point O is equal to the moment of force F2 about point O plus the moment of force F1 about point O. So over here, this is the moment of F1 about point O, and here is the moment of F2 about point O. And then we can perform vector addition. So this is the general formula. And in 2D, usually it's easier to just apply the scalar formulation. We just calculate the magnitude of the moment, and then the direction will be either clockwise or counterclockwise. So in this case, if we resolve the force F into two components, F of x along the x direction and F of y along the y direction, then we'll take care of the two component forces separately to calculate the moment about the point O. So with scalar formulation, force F1 has a moment arm of, so again, moment arm is the perpendicular distance from the point O to the line of action. So we drop a perpendicular line from point O to the line of action of F of x, and this distance will be d of x and equal to y. And with our right-hand rule, this F1 will cause a clockwise rotation into this direction. For force F2 though, if we draw a perpendicular line from point O to the line of action of Fy, so the moment arm of Fy is x. Use right-hand rule, Fy will cause a counterclockwise rotation. So both forces will cause rotational effect, but they will cause rotation in opposite directions. Therefore, the resultant moment will be Fx times y, which is the moment of force Fx about point O, subtract, because they have opposite effect about point O, Fy about point O. And the result, since we are using moment of Fx as the positive, so that means your final result, you need to indicate this moment has clockwise rotation, or the number indicates a clockwise rotation. Because again, we are treating the Fx moment as a positive value in the opposite direction as a negative value. But usually in 2D, we do have this sign convention. Counterclockwise rotation will be positive, or moment cause counterclockwise rotation will be positive moment, and clockwise rotation will be negative moment. And we rewrite this principle of moments. The resultant moment is determined by finding the algebraic sum of the moments caused by all the forces in the system. Again, this is only valid for a 2D problem. And also keep in mind, when this moment causes counterclockwise rotation, we are going to use positive F times D. And if this moment causes clockwise rotation, then we need to use negative F times D. And in this case, in this whole system, we have three forces, F1, F2, and F3. So it seems like F1 will cause counterclockwise rotation, so it will be F1 D1, and F2 causes clockwise rotation, so minus F2 times D2, and F3 has counterclockwise rotation effect as well, so it's a positive moment. Well, finding the moment of a force in 2D is straightforward. We know the perpendicular distance d. But finding the perpendicular distances can be hard, especially when you are working with forces in 3 dimensions. So a more general approach to finding the moment of a force exists. This more general approach is usually used when dealing with 3-dimensional forces, but can be used in 2D cases as well. And this more general method of finding moment of a force uses a vector operation, which is the cross product. So the moment of a force about point O is defined as a position vector R cross the force vector F, where this position vector is directed from point O to any point on the line of action of F. So be very careful with the orientation of this position vector R is from. So the tail of this position vector is the point O, and the head of this vector R is on the line of action of force F. Keep in mind that for cross product, R cross F is not equal to F cross R. So remember, to calculate the moment of force about the point O, it's R, position vector, cross force F. And after we write the cross product in 2x2 determinants, we can solve the moment of the force F about point O in Cartesian form. And remember, the principle of moments still applies when you use the vector formulation, meaning when you use the cross product to solving for the moment about the point O.